In this video, we are going to discuss vectors. A scalar is a quantity which has only magnitude. Example, temperature, mass. A vector is a mathematical object which has magnitude and direction. Examples, velocity and force. The general vector notation in an n-dimensional space is given by where AI is called as the component of the vector. And the representation of vector in 2D space as a line segment which is going from A to B, from A as x comma y to B A x plus A comma y plus B. This can be shown by consider this is my A, which is x comma y to B plus B. This is AB. An important point. Whenever a parenthesis is used to represent, it's a coordinate, and the vectors are represented by this. Now, let us consider a three-dimensional coordinate A1, A2, A3 and B1, B2, B3. Then the vector A to B can be determined by similarly, if the direction is from B to A, then please note that direction is important while calculating a vector from a given coordinate system. Now, the magnitude of a vector V, A1, A2 and A3 can be given by A1 square plus A2 square plus A3 square. And a unit vector. Any vector whose magnitude is 1 is called a unit vector. And a vector which consists only zeros is called as a zero vector. Now let's see standard basis vector. So we have the principal axis I, J and K. This can be provided by 1 0 0. For J it's 0 1 0 and K is 0 0 and 1. That's in the three-dimensional space, and this can also be represented in the two-dimensional space. And one of the property with the standard basis function is, let us consider a vector A1, A2, A3 utilizing the standard basis in the principal direct axis as A1 0. Three. This can be given by I, J and K. Now, vector addition. Let us consider there are two vectors A and B. Now, the vector addition is provided by similarly for a vector addition, say 1 plus b1 vector subtraction is provided by a1 minus b1, a2 minus b2, a3 minus b3. And for scalar multiplication, let us consider this vector a. So when we multiply a scalar to a vector, this gives us now let us see some properties of vectors. V bar plus W bar is also equal to W bar plus V bar. And when U plus V plus W, it's also equal to U V plus W. And when we multiply a vector with a zero vector, when we add a vector with the zero vector, the output would be the initial vector. When we multiply a constant to a sum of vectors, we get, and when we multiply a 1 to a vector, unit vector, we still get the principal vector, and a plus b v bar is given by a v bar plus b v bar. Now let us see dot product. It's also called as a scalar product or inner product as well. So how do we calculate? Let us consider two vectors a bar and b. So the dot product of these two vectors is provided by let us see an example. We have two vectors 2, 4, 5 and 8, 3, 1. Let's calculate the dot product of these two vectors. Let us also see it in another format representation, that's in the standard basis vectors. So when we have two vectors of this format, the dot product will be the products using the coefficients of the principal axis. So this would be minus 2, 4 into 1 plus minus 6 into minus 8, 4, 46. Let us see some properties of dot product. U dot U V plus W is V plus dot W C V dot C W bar, and it's also equal to C times, and the direction is interchangeable. And dot product, a dot product with the zero vector would be 0, and multiplying, taking a dot product with the same vector will yield, and if the dot product is 0, then the vector would be a 0 vector. Now let's talk about projections. Let us consider there are two vectors a and b. So the projection of the vector b onto the vector a is provided by the formula a bar dot b bar, a dot product of the two vectors, magnitude squared of the vector a multiplied to the vector a. This is a normal multiplication. Similarly, projection of a bar onto b bar is provided by dot product b bar. Let us see an example. we need to calculate the projection of A bar 2, 4, 6 onto B bar 6, 4, 6 minus 4 and 2. So now the projection of A on B is provided by the formula A dot B by magnitude of B square and into B. So let us first calculate the dot product of A and B, that is 2 into minus 4 plus 6 times minus 2 this is minus 12. Let's calculate the magnitude of B, that's minus x whole square .56, and the square of magnitude would be 56. So now let's calculate the projection of A on B. Dot product is minus 50 by 56 to the vector B. 6 minus 4 minus 2. We're doing some math, we get 5.35, 0.57, 58, because this is, we're doing a constant to a vector. So just multiply each element with the constant. So now let's talk about some direction cosines. Let's consider a vector u in the three-dimensional space provided by this diagram. So the angle, the vector makes an angle with each principal axis. So alpha, let us consider that the vector u makes an angle alpha with x-axis, beta with y-axis, and gamma with z-axis. So these alpha, beta, and gamma are the direction angles, and cos alpha, cos beta, cos gamma are the direction cosines. And we can calculate the direction cosine by the following formula. Cos alpha is provided by vector multiplied by the standard basis dot product and then the magnitude of u. One thing, when we take a dot product of the vector with its bases, that would be u1 into 1 plus 0 plus 0, it's u1. So we can calculate by the component u1 by the magnitude of u, the vector u. Similarly, and now some properties. The vector w, which consists of the direction cosines, is a unit vector because when we take the magnitude beta plus cos square gamma, this is 1, and magnitude a cos alpha, cos beta, and cos gamma. Vector A is also provided by the magnitude of A generally multiplied with the vector W. So let us consider, we need to find the direction cosines and the direction angles for the given vector u, 3, 0, and 4. First, let us calculate the magnitude of U. Phi is 5, and then cos alpha is 5. The first component U, that's 3 with a magnitude 5. And cos beta is 0 by 5. Cos gamma is 4 by 5. These are the direction cosines, and the direction angles are provided by inverse of 3 by 5. So when we calculate this, we usually get the answer in the radians. If we convert it into degrees, it would be 53. And here beta would be pi by 2 or 90 degrees. And gamma is now let's talk about cross product. When we have two vectors a bar and b bar, the cross product of a cross b is provided by using the principal basis axis. Write down the components of first vector followed by the second vector. And once you find the determinant of this cross product, once we find the determinant, we'll get the cross product of a cross b. Let us see this with an example. We have two vectors a bar and b bar. Let's calculate the cross product of these two. Let's write down the basis vector and 2. Now, and also one important thing is the sign convention. This would be plus, minus, and plus from the cofactors. And now let's find the determinant. For I, 1 into 1 plus 4 minus j is 2 minus 3 plus k is 4 to the 8 minus of 9. So this is phi I plus j plus 11. If theta is the angle between two vectors a cross a bar and b, and if the angle lies between 0 and 180, then the cross product, the magnitude of the cross product a cross b is given by magnitude of a, magnitude of b, and sine t. And the direction of the cross product a cross b to the original vectors a and b can be found by using the right hand rule. It will always be perpendicular to a cross b. When a bar and b bar are parallel to each other, that is when the angle between them is 0 or 180, then the cross product, the magnitude of the cross product a cross b will be 0. And if a cross b is 0, then a and b are parallel, else a cross b is orthogonal to a and b. Let us see this with an example. A plane is defined by the coordinates p, q, r. Please pay attention, these are the coordinates, not the vectors in the three-dimensional space. And we need to find the vector orthogonal to the plane. So first we need to calculate the vectors for q. which is given by and then vector q2r to -1. Now the cross product of q this is given by I times 2 plus 2 minus j 0 minus 1 plus k minus 1. That is 4i plus j minus k. This is the a vector orthogonal to the plane given by the coordinates p, q, and r. Now let's see some properties of cross products. U cross v is p cross u, and u cross v plus w is given by u cross v plus u cross w, and c is a constant. C u cross w is provided by u cross c w bar, or constant c u cross w, and u dot v bar cross w is also equal to u cross v dot w. This is also equivalent to I hope this helps, and thank you.